We've looked at a lot of different titration reactions, reactions of acids and bases, and it's important to note that all of those reactions take place in water or aqueous solution. In fact, this chapter is entitled Aqueous Ionic Equilibrium. And if you remember back to the first semester when we talk about solutions and we are introduced to molarity, and that's when we are told that not all ionic solids are soluble, and you're given or you're taught about the solubility rules. I have the table from that chapter here, and so what that means is if we have two solutions, like let's say we have sodium chloride, and we know sodium chloride is soluble because we see the symbol AQ. That does mean we have sodium and chloride ions, and that we know by now. I've hammered this through my lectures. And if we have another solution with silver nitrate, for example, which is also soluble, we now look at the solubility rules and we can determine that, well, not all chlorides are soluble. There are some exceptions. Silver, lead, and mercury, and those would precipitate out. So if we have a solution in a test tube of sodium chloride and silver nitrate, and we mix them together, we would see a white precipitate forming, and then we would write it as AgCl with a phase label S, right, the solid, and then our spectator ions are sodium and nitrate, and we write them together in the molecular equation with the symbol AQ. You understand that the net ionic equation is between silver ions and chloride ions, and we are forming that solid, and you can visually observe that when you mix those two solutions. But it is true that not all of that silver chloride is in the form of the solid. There's still a little bit that dissociates into silver ions. It's just not very little. Right, and plus, so there is this equilibrium reaction of silver chloride. So a little bit of silver. What that says is that all of those ionic solids are soluble to a certain extent, right? And so now what we get is an equilibrium expression, right? K, and so we know how K, the equilibrium expression of K is. It's going to be products over reactants. And this one is simple. It's just 1-to-1, and we are not including the solid because the solid is there is in excess. Okay, and so this gets for acids and bases we have a Ka, and for just general equilibrium constants we do Kc or Kp for gases, and so this gets the little Ksp, solubility product, right? And so those are usually very small, and we call that the solubility product, and we can do calculations with that. Before we do calculations, let's practice setting up the equilibrium expression. So for example, if we had lead 2 chloride, we know that lead 2 chloride is insoluble. However, it does have a solubility product where we produce some lead 2 ions and chloride ions in solution. So those are aqueous, and so there's a Ksp, an equilibrium constant associated with that. And it's also important to remember and recall that there are 2 chloride ions for every 1 molecule or 1 unit of lead chloride. And so the Ksp expression is then simply equal to the lead concentration times the chloride concentration squared. Simple as that. And for this particular compound, you see the Ksp is 1.17 times 10 to the minus 5, so it is for all practical purposes not soluble, and that's why we have the solubility rules. And if you do have a considerable source of lead and chloride, it will probably precipitate out, but a tiny little bit stays behind. So here's the equilibrium expression. So this is just a general dissociation equilibrium expression for it. It fits any ionic compound that's insoluble. So just to make sure that you understand that, let's put not the nitrate, of course, it's lead 2 chloride. So here M would be PB, N would be equal to 1, right? Because there's just an imaginary, no, there is a 1 there, it's not imaginary, we just don't put it there. X would be the chloride, and then M would be B2, and so this is how you come up with, this is just a generic solubility product expression, okay? This is a table of various different KSPs, and I give you the table, of course, for all your calculations if that is needed, unless I ask you to calculate the KSP, which we will look at here in a minute. There's really a wide range of solubilities, 10 to the minus 5 compared to 10 to the minus 19. There's a huge difference there. So if you have like iron sulfide or iron hydroxide, iron 2 hydroxide, you have a very few, the solubility of that is very, very small. Speaking of solubility, there's a difference between molar solubility and the KSP, but there is a relationship, right? Molar solubility is what is our concentration and molarity, or maximum concentration possible. Okay, so for any of these solids, and I think it's better to look at a real example. So if we had lead chloride and we split that into lead ions and chloride ions, our solubility would be, of course, if we have an amount of lead here, lead chloride, and so some amount will split. Let's call this X for now, and then 2X, right? So if you dump a kilogram of lead chloride into a liter of water, of pure water, you're going to have some dissolve, and so that we name that the amount X, right? So this will go down by X, this lead, but it's going to be insignificant again because it's the excess amount of solid will still be remaining in that solution even if we add an entire liter. So but this goes up by X and this goes up by 2X, and so if we call that the solubility, instead of S we just call this, instead of X we just call this S, so to indicate this is the solubility, and 2S. And all you do is you plug that into your KSP, so your KSP would be equal to S times 2S squared, and so you get a KSP equals to 4S cubed, and then, you know, so what they're saying is it'll always be, look, if you solve for molar solubility, let's call that S, it will, in this case, S is going to be equal to the cube root of the KSP over 4, okay? And this is again generic, but you will always be given a real example, and you should be able to work it, right? So let's work an example with lead chloride. So half the problem I already solved. So if we call the molar solubility S, which is the maximum amount that you can dissolve, and so the volume doesn't matter whether you have a half a liter or 15 milliliters, your molarity is always going to be the same. Of course, it's temperature dependent, and so at the same temperature. So if we have an excess here, so if we set up some sort of ice table, we can do that, and we call the molar solubility S. Initially we have no lead and chloride ions, and so then that's going to go up by S, and this is going to go up by 2S, and so we end up with S and 2S. And if we plug that into our KSP, the KSP is equal to the lead concentration, that's lead 2, times the chloride concentration squared. And as long as we have no other ions present, so if we have pure water here, S is going to be equal to the concentrations here at equilibrium. And so we can say that the KSP equals to S times 2S squared, and so the KSP equals 4S cubed. Now if we have any source of chloride or lead already in solution, let's say we want to calculate the molar solubility of lead chloride in ocean water, right? Ocean has chloride already present, so we need to take that into consideration. Our molar solubility is going to be much smaller, right? And that's because we have chloride present, so this equilibrium can then not shift as much to the right as it could in pure water. And we'll look at one of those examples in a minute as well. But we can solve this one real quick here. We can say that now S, I'm going to solve for S. Okay, so I know what KSP is. So S is going to be equal to the KSP, which is 1.17 times 10 to the minus 5. I'm going to divide by 4, divided by 4. And then this is the third power, so I'm going to do the cube root of that expression, and then if I put this into the calculator, S is going to be equal to 1.43 times 10 to the minus 2 m. So again, that is the maximum molarity possible of lead chloride in pure water. There it is. And yeah, let's look at a slightly different problem, but again, just in pure water. So it's the same idea. We have a different solid now. We have silver sulfate. It has a different KSP. We can look it up, but I'm asking you to calculate that based on the molar solubility. So you provide it with the molar solubility rather than the KSP. So there, make sure that you know the difference between KSP and S, right? Molar solubility product versus molar solubility. But we have the same idea. We have a KSP, and the KSP is going to be equal to the silver concentration squared in this case times the sulfate concentration. And of course the concentrations are related to the molar solubility, because this is going to go up by 2S, this is going to go up by S. So the KSP will be equal to 2S squared times S, basically the same thing, except this time the cation is the one that has dissociates too, but they're interchangeable, where the molar solubility in this case works out to also be 4S cubed. And so if I now I know that the KSP, I know what S is, I just plug that in. So the KSP equals 4 times the molar solubility, which I'm going to have to look, 1.4 times 10 to the minus 2 to the third power, and if I multiply that out, I get 1.1 times 10 to the minus 5. I guess we should go back to the table, see if a silver sulfate is here. It is not, all the silver compounds. So okay, so you can probably Google it. Okay, anyway, what we can also do is look at a solution that already has a common ion present, right? So for calcium fluoride, for example, first thing you can do is before you look at it, you can write down the KSP expression. It's probably a good idea. KSP is going to be equal to the calcium times the fluoride concentration squared. So we know that. And so for the molar solubility, it's a little different, because sodium fluoride has sodium ions and fluoride ions. Okay, that's a soluble compound. All sodium solids, compound or ionic solids, are soluble. So we have 0.1 molar concentration of fluoride already before it shifts, right? So we have none of that and 0 calcium ions in this solution, but we already have 0.100 m molarity of fluoride. Okay, so but then everything else happens the same. This will shift to the right, it'll produce some calcium, and it'll produce twice as much fluoride. And at equilibrium, we then have S, and then 0.100 plus 2S, and we can plug that into here. So the KSP is going to be equal to S times 0.100 plus 2S squared. We solve for S. S is going to be equal to the KSP, which I can look up. I have it on the next slide, divided by 0.0100, which is equal to 1.46 times 10 to the minus 8 m. So this is the molar solubility in this scenario here. So here's that KSP that I missed earlier. You look it up, or I provide it to you, and then you just plug it into this equation and solve for S in this case. Again, molar solubility is what we're asking for. And so it makes sense that the amount that splits apart is the same to S and S, and thus that it simply adds to the existing fluoride concentration already. So you always want to look for common ions present in these problems. So finally, just a food for thought here: determine whether each compound is more soluble in acidic solution, neutral solution, or a basic solution. So what we're looking for is whether an acid or a base will react with either the cation or the anion. So in the case of silver, we have silver ions and iodide ions, and so this one is a little harder to see, but silver is a Lewis acid, so silver will actually react with a base. In fact, with a strong base, it makes a complex ion, AgOH2 minus. And so in basic solution, silver iodide will be more soluble. This one is easy, calcium hydroxide. The hydroxide is a base, so in acidic solution, you will have a higher solubility. So iron carbonate, remembering that carbonates are bases, hydrogen carbonate and carbonic acid. So this will react with acids, you might remember, to form carbon dioxide and water. So it'll be more soluble in acid, barium fluoride, barium and fluoride ions. Oh shit, I got the headphones on. Alright, we'll see if that works or not. Anyway, so fluoride is hydrofluoric acid is weak, therefore if this is a conjugate base, it'll be more soluble in basic solution. And again, a tricky one, lead is a conjugate acid, and lead will actually do the same thing that silver did. In fact, it'll react with 4 hydroxides to form a complex ion, PbOH4, which will have a -2 charge. So in a basic solution, lead to bromide will be more soluble. So just a conceptual thing. This is the end of the chapter. I'll see you for thermochemistry.